Okay, so uh, first thing is we have a test on Friday, right? Friday? I didn't look, but I think that's right. Okay, so exam one is Friday, and I want to see what we get through today before I decide for sure what topics it's going to be up through. Um, but it'll definitely have at least a little bit of the stuff in strain and constitutive relationships. We'll see. We'll see how far we get today. Um, Anybody have any homework questions? Okay, good. Thumbs up. Okay, so we talked about, so last time, well, first we talked about um, the four main assumptions in this class. Um, and those are, we're going to assume small deformations. We're going to assume linear elasticity. Um, which is the same thing as saying the compliance matrix and therefore the stiffness matrix are constant matrices. Uh, and then we're assuming that the material is homogeneous. So any material that we're looking at is made out of a single thing. It's the same at every point. And then it's isotropic, which means that at a single point, the behavior is the same in every direction. That doesn't mean geometrically it's the same in every direction. We'll deal with a lot of different kinds of shapes, but it's saying that the material itself has the same material properties any direction you look. And we got this form of the compliance matrix that was one. Am I really going to write this all again? It looks like it. I don't know. 1 over E, negative nu over E, negative nu over E, 0, 0, 0. And then negative nu over E, 1 over E, negative nu over E, 0, 0, 0. Then negative nu over E, negative nu over E, 1 over E, 0, 0, 0. And now we get to the ones where all the terms that are multiplied by the normal stress are 0. And now we're just dealing with the shear stresses. And so we have 2 times the quantity 1 plus nu over E, 0, 0. And then that term just keeps going along the diagonal. And one of the questions in the homework that I assigned, like, I don't know, this morning or last night or something, I don't remember, way too late, was now you use this matrix if you know the stresses, and then you multiply the Voigt stress to this, and you get the Voigt strain out as the output. So what, based on this matrix, what are the stress elements that matter if you're calculating the normal X strain, if you're calculating the elongation or contraction in the X direction, what stress elements matter? You see that from the form of the matrix. So if you're multiplying this matrix times EXX, EYY, EZZ, and then the shear, no, this is stresses. Sigma XX, sigma YY, sigma ZZ, and then the shear stresses, okay? Then what happens is when you do the matrix multiplication, you multiply this times sigma XX plus this times sigma YY plus this times sigma ZZ, okay? And that that big dot product is what gives you the EXX element of the Voigt strain. You see what I'm saying there? So the only stress elements that come into EXX, the X element of the Voigt strain, are the three normal stresses. Okay? Everything else is multiplied by 0, so it doesn't come in. Okay? What about the YY strain? What stress elements affect the YY strain? Yeah. I'm sorry. Oh, yeah. Well, you take, so what you do here is, I'm going to erase all this. So you're multiplying by this vector. Okay. And so to get the first element of the output Voigt strain, you take the dot product of this with this. Okay. And so that dot product says sigma XX times 1 over E plus sigma YY times negative nu over E plus sigma ZZ times negative nu over E plus 0 plus 0 plus 0. And so that gives you the value of, so in other words, let me erase this before I forget. So what this says is the X normal strain is equal to 1 over E times sigma XX minus nu over E times sigma YY minus nu over E times sigma ZZ. Okay. The Y normal strain is equal to negative nu over E times sigma XX plus 1 over E times sigma YY minus nu over E times sigma ZZ. And the ZZ normal strain is negative nu over E times sigma XX minus nu over E times sigma YY plus 1 over E times sigma ZZ. Okay. And so no matter what the shear strain, the shear stresses are, you know, it could be bent all out of shape. That just doesn't factor into the normal strains at all. That doesn't have any effect on the elongation or the contraction. Okay. The shear stresses and the shear strains relate to each other, and the normal stresses and normal strains relate to each other. One thing interesting about this, though, is you might think, just off the top of your head, like, well, what determines the elongation in the X direction? Well, probably just the loading in the X direction, right? I mean, if you stretch, apply a tensile load in the X direction, then that makes it elongate, right? So what's going on with these? Exactly. So these are the Poisson's effect. All the ones with the news in them, what that's saying is, so if you stretch it in the x direction, if you tug on it in the x direction, it elongates it, and that makes sense. But it also says if you compress it in the y direction, that Poisson's effect makes it bulge out in the x direction too. And the same thing with the z direction. Compress it in the z direction, it makes it bulge out. And all of those three things combine to give you the elongation. Okay. Okay, so now what about shear strains? Factors into the YZ shear strain. Remember, the YZ shear strain tells you what the angle is between the positive Y and positive Z faces. So what factors into that? And so it is so the normal stresses don't matter. That's right. But notice that the reason that all three of these matter is because we have for the normal strains is because we have non-zero values in all three of these spots. When we get to the shear strains, we don't have dependence on anything except the the corresponding shear value. There's no equivalent of like a Poisson's effect for shears. Okay, so the only thing that affects the YZ shear strain is the YZ shear stress. Okay, and same with XZ and XY. So this is equal to 2 times the quantity 1 plus nu over E times tau YZ, and that's all. And so none of the other angles have any effect on that one. If you're interested in how the angles are going to change between the Y and Z faces, all you care about is the YZ shear stress. And might as well finish writing this. So XZ is equal to 2 times the quantity 1 plus nu over E times tau XZ. And XY strain is equal to 2 times the quantity 1 plus nu over E times tau XY. That's what that matrix is. Yep. Right. That's right.
You want us to use tau?
Either one's fine. I want you to just feel good about your decision. All right. Well, in order to come up with this compliance matrix, we need to come up with a value for Poisson's ratio and Young's modulus. And so I'm going to do an example now where of like how you get that out of a tensile test. What do you have to do? Okay, so example. So this is a tensile test, and it's the sort of the most basic material testing measurement that you do. Like when you get this new material, you have a certain kind of plastic or whatever, you take this thing, you put it in a tensile testing machine, and you do these measurements. Okay, so let's say we have a thin plate. And before it's deformed, this length is 10 centimeters, 0.1 meters. This thickness is 1 centimeter. 0.01 meters. And then this length is 2 centimeters, not drawn to scale. And then we apply loads to this to stretch it. That's the tension in the tensile test. And let's say the magnitude of that load is 5,000 newtons. What's the load on the bottom of that piece? Yeah, otherwise it would accelerate, and that would make it really hard to take the measurements. And what coordinate system do we want to use? I sort of mentioned this in passing. Yeah, well, so yes, we want the loaded axis to be the x-axis. The other ones we don't really care about. Ones I have drawn in my notes are y like this, and then z coming out, so I'm going to use that. And under this 5,000 tensile loading, the length so I'm going to call this L, and I'm going to call this W. L, is that going to get a little bigger or a little smaller? Bigger, yep. So that becomes 0.10, let's say 3 zeros and then a 3. And W, is that going to get a little bigger or a little smaller? So let's say that's 0, 0, and then 3 nines and a 2. And we want to figure out the compliance matrix. And notice that these things that we have to measure are all pretty easy. I mean, definitely by like engineering standards, those are easy things to measure. I mean, we're talking about very small changes in length, so it has to have good precision, you know. But it's easy to measure that force that you're applying. It's easy to get calipers that can carefully measure the changes in width and the changes in length. Okay. I guess it depends on what your sample piece is. Really, anyone who does a lot of this has a machine that's made just for this, and it does the measurements itself. MTS, have you heard of MTS? It's in the Twin Cities somewhere. Yeah, and oh yeah, okay, cool. And they started out as the main supplier of machines that did this kind of stuff. And in fact, I mean, the same way like you you know, people if they want a cola, they order a Coke or whatever. Like that's what you said. Like, oh, you guys have an MTS machine? We could measure the. Now they do all sorts of other stuff, but. That's what started. Okay, so how are we going to measure this? Well, remember that Young's modulus is the stress along the loaded axis divided by the strain along the loaded axis. So we have to take those two measurements. And Poisson's ratio is You can do it two ways. We can do it as the negative YY strain over the loaded axis strain, or as the ZZ strain. So either one of those off-load strains divided by the loaded axis. That shouldn't say ZZ, that should say XX. Okay, we're just, because that's just a measurement of how much bulging or sucking in the material does when you load an off axis, a different axis. All right, so what do we need? We need sigma XX, we need EXX, and we need EYY or EZZ. So first, let's calculate sigma XX. And the way we're going to do that is this is just going to be the force divided by the area. And you want to think about the area that's resisting that load. So we don't care at all about the length here. All we care about is this cross-sectional area. If that's fatter, it's going to be harder to stretch this thing with 5,000 newtons. It won't stretch as far. If it's skinnier, it's going to stretch more. Okay? That's why, like, strong people, you can tell how strong they are because you can see the increase in cross section, like me. Okay? That's what that is. When you work out, you get a bigger cross section, so you're, it's easier to provide that force. Okay, so the force is 5,000 newtons. The area, what matters for that area, and we're going to use the original area, not the deformed area. There's not, since we're assuming small deformations in everything we do, it's not worth making a big deal out of that. They're basically the same as the idea. So the area we want is 0.01 meters times 0.02 meters. And so you get 2.5 times 10 to the 7 pascals. And then the strain along the x-axis. So the strain is the deformed length minus the starting length, the unloaded length, divided by the starting length, the unloaded length. Okay, so we want only the x values. So along the x-axis, what's the deformed length? That's right, 0.10003. And so then the undeformed length is just 0.1. And then we're dividing by 0.1. And you get a value of 3 times 10 to the minus 4. And strain doesn't have any units. And now the only thing we still need is strain for one of the off axes. We were given the change in length or the new length for the y. So we'll use that. So sigma yy is equal to so the deformed length was 0.00 and then 3 nines and then a 2. Is that right? And the starting length along the y-axis was 0.01. And then we'll divide by 0.01. And we get a negative strain, and it's -8 times 10 to the minus 5. Okay, so now we can use these measurements that we took to do the calculation. The Young's modulus is 2.5 times 10 to the 7 pascals over 3.0 times 10 to the minus 4, and that's unitless. And so you get a Young's modulus of 83.3 repeating times 10 to the 9th pascals, or 83.3 repeating gigapascals. Did you get that? Did you do it? Okay. Any questions about that calculation? And that's the stiffness of the material. So diamond has a much higher value than that. Silly putty has a much lower value. Okay. Did I? Oh, I didn't put enough nines in. Oh, okay, go back and change this. I need it to be this for it to work. I should have put 4 nines here, I guess. Okay, so this has to be that. And now the numbers work out, hopefully. Okay. Okay, Poisson's ratio. So this is going to be negative strain for the off axis, so negative 8.0 times 10 to the minus fifth, divided by the strain for the loaded axis, 3.0 times 10 to the minus 4. And so you always get a positive value for Poisson's ratio. And this one comes out to be 0.26 repeating, which is right in the ballpark of what you expect values to be for concrete or metals. And so now we want to fill out the compliance matrix. So there are only 3 different elements that you can have in the compliance matrix. The first one, so now we're calculating the compliance matrix. 1 over E is, so 1 over what we just calculated. Nope. So 83.3 repeating times 10 to the 9th. And so you get a value of 1.2 times 10 to the minus 11. And then one of the other 2 types of values you have in the compliance matrix is negative nu over E. So that's negative 0.26 repeating divided by 83.3 repeating times 10 to the 9th. And you get negative 3.2 times 10 to the minus 12th. And then the only other one is 2 times the quantity 1 plus nu divided by E. So that is 2 times 1.26 repeating divided by 83.3 repeating times 10 to the 9th. And that is 3.05 times 10 to the minus 11. And what are the units of the compliance matrix? It's like, look at this one, it's 1 over pascals, so whatever that is. In this case, it's meters squared over newtons, or 1 over pascals. And they all have the same values because all stresses have the same values and all strains have the same. So all of the elements of a compliance matrix for any materials we're going to deal with, if you're using SI units, they're going to be tiny. Does that make sense? I mean, to me, it makes sense. Think about it this way. Imagine, so close your eyes for a second. We're going to do an imagination exercise. So now imagine like you have a baseball-sized piece of steel. That's the material we use the most. And imagine someone's like, 10 feet away from you and this thing at your head. And imagine your first thought when this ball of steel hits your head. Are you like, wow, that was compliant? If that's not your first thought, then those values should be small. So on the other hand, if you filled out the compliance matrix and then took the inverse of it and got the stiffness matrix, would you expect those values to be big or small? Those are big. Exactly. Okay, so the compliance matrix finally is so 1.2 times 10 to the minus 11, negative 3.2 times 10 to the minus 12, negative 3.2 times 10 to the minus 12, and 3 zeros. And now the next row, negative 3.2 times 10 to the minus 12, 1.2 times 10 to the minus 11, negative 3.2 times 10 to the minus 12, and 3 zeros. Next row, negative 3.2 times 10 to the minus 12, negative 3.2 times 10 to the minus 12, 1.2 times 10 to the minus 11, and 3 zeros. And now for these, we have mostly zeros. There's just one single element that keeps moving along the diagonal that's non-zero. And that has a value of 3.05 times 10 to the minus 11. Remember, this is an easy place to make mistakes because a lot of times elements of the compliance and stiffness matrix or stress values are given in megapascals or gigapascals or whatever. So the units of the compliance matrix must be the reciprocal of the stress units that you're using to multiply. And if you ever calculate the strains for a problem and you get values that are like something times 10 to the minus 10 or minus 11 or minus 12, those are probably too small, and probably the thing was you used stresses that were in megapascals and a compliance that was in 1 over pascals. Okay, so those units have to agree. So now let's do another example. Oh, I wanted to say, so as a ballpark, like what kind of material would have a value like this? Would have values like this? A Young's modulus of 83.3 repeating gigapascals is like right in the ballpark of like copper. This is a little softer material than copper, but within 10% or something. Um, Steel has a Young's modulus of about 200 gigapascals. So steel is a lot stiffer than this. I don't know what it is off the top of my head, but you know, you can always just Google Young's modulus diamond, like whatever material you want, and a bunch of stuff will pop up, and hopefully they'll all agree with each other. If they don't, you need to look into it farther. Um, Diamond, it's higher, a lot higher, but I don't know what it is. Um, okay, so let's say now a single point inside the material tested above um, has the stress tensor sigma is equal to 2 times 10 to the 7th, negative 1 times 10 to the 7th, 0, negative 1 times 10 to the 7th, 0, 0, and then the last row, 0, 0, 8 times 10 to the 6th. And this is in pascals. What is the resulting strain at that point? Well, the Voigt strain is just going to be equal to that big compliance matrix. I'm not going to write out all the values again, but this big 6x6 compliance matrix we just figured out, and then multiplied by the Voigt stress. And so the Voigt stress is the x normal stress, so 2 times 10 to the 7th, the y normal stress, the z normal stress, and then the yz shear stress, the the xz shear stress, and then finally the xy shear stress, negative 1 times 10 to the 7. And if you multiply this out, you get 0.000214 negative 0.40 and then 896 and then positive 0.40 and then 32 and then 0, 0, and the last one is negative 0.30304. And then based on the meaning of all these different strain values. Now you can visualize, if you imagine that material point as starting as a cube, you can visualize based on this what happens to it. So first, the normal strains are elongations and contractions. What's happening along the x-axis? Is it based on if it is loaded in the way given by that stress tensor? Is it elongating or contracting along the x-axis? That's right, it's stretching. And along the y-axis? Contracting, yep. And z-axis? Right. And now we're thinking of starting it as a cube. So in the YZ plane, those angles that start out at 90 degrees, they're still 90. So we're going in this funny order again, remember? So that's the fourth value here is the YZ strain. So that's still 90. What about XZ? Still 90. And then XY, is it more acute or more obtuse? Obtuse. Acute is positive, so that angle between the positive X and positive Z face is getting more acute. And if you, more obtuse, sorry. And if you spend a little time sketching this thing out, you could sketch out what this cube looks like now under this loading. Any questions about that? Yeah. Oh, yeah. We are, if you loaded the material as a with point forces, that's what it would do. But we're always making the assumption that all of this stuff is happening as a uniform distributed load, and if you did that, it would stay like a parallelogram. Yes. Mm-hmm. Yeah, that's what I would always do because that's such a tiny angle you can't see it. Same with the length changes. So you can't see any of these changes, but I would draw it like really long this way and really short this way. And yes. Yes. Yep. And that's one of the million places that that we're depending on small deformations because that all comes from sines and cosines and stuff, and it gets a lot more complicated if you don't have. So that's making the small angle approximation of a sine as being equal to the angle in radians. If you get into 10, 20 degrees or whatever, big deformations, this really isn't a good representation of the angular change anymore. All right, the next thing that we're going to talk about is stress transformations. I don't think I'm going to get into the calculations yet. But the idea with stress transformations is given a stress tensor using one coordinate system, so representing one coordinate system, determine the stress tensor in another coordinate system. You've probably seen this done with vectors before. So you're sort of familiar with this idea. Familiar this for vectors. So, for example, let's say that you have a vector like this with a length of 10, and it makes an angle of 30 degrees with the horizontal. And in a coordinate system like this, where that's the x-axis, that's the y-axis, components of this vector are 10 times cosine of 30 degrees, 10 times sine of 30 degrees, and I'll put 0 for z since this is in the plane. And so this comes out as like 8.6650. But now we want to take that value in this coordinate system and answer the question, what are the components in a coordinate system yes, where this angle is 30 degrees? Well, it's pretty easy to see what it should be because this vector is just pointing, in the new coordinate system, this vector just points straight along the x-axis. So the components of that vector in this coordinate system should be 10, 0. Okay. Everyone with me on that? But the question is sort of like, what's the, how do you do that calculation? And the way you do it is you use a rotation matrix. And I always think of it like this. We want to multiply by a rotation matrix whose columns are the axes of the original coordinate system expressed in the new coordinate system. Okay, so our rotation matrix Q is going to be, so the first column of this matrix is going to be, what are the components? So now think of these axes as unit vectors. Okay? What are the components of the unit vector in this direction if this is your coordinate system? Give you 0.866, cosine of 30, and then negative 0.5, and then 0. If this was important, I would do this more slowly. You don't have to do it like this. I'll give you formulas for this. But now the y axis, what's this unit vector expressed in that coordinate system? Positive 0.5, positive 0.8660. And then the z-axis stays the same. It's the same in both of them, so that's just 0, 0, 1. And so now the vector in the new coordinate system is equal to this matrix times the original vector, that vector in the original coordinate system. What was that? 8.6650. If you multiply that out, let me just make sure this works. Yes, you get 10, 0, 0. Okay, so that matrix has the effect on vectors of re-expressing them in some chosen new coordinate system. And you use it for vectors like this. You also use it to do it with tensors. You just use it a little bit differently. So that's what we'll talk about next time.